All right, today we're diving into something pretty incredible at the crossroads of neuroscience and engineering. It's a story about a device that doesn't just treat an injury, but actually teaches the brain to heal itself from the inside out.
So let's just start with the huge central question that drives this whole thing. What if, instead of just trying to fix a damaged spinal cord, we could go straight to the command center, the brain, and teach it to find a new way around the injury?
You know, at its core, a spinal cord injury is really a communication problem. Think of it like this. The brain, the CEO, sends a clear order, walk. But that message gets garbled or completely lost on its way down the spinal highway to the legs. And the result? A loss of that voluntary control. Now this is huge. And it's really the secret sauce to this whole thing. See, in 70% of spinal cord injuries, the cord isn't completely severed. They're called incomplete, which means some nerve fibers, some tiny pathways, actually survive. They might be weak, they might be faint, but they are there. And that little bit of hope is everything.
This idea totally flips the old way of thinking on its head. For so long, rehab has focused almost entirely on the spine. But this research says, wait a minute, let's change our target. Let's reinforce the command right from the source, from the brain itself. The goal isn't to rebuild the broken highway, but to give the signals trying to cross it a massive, supercharged boost.
Okay, so how on earth do you boost a brain signal? Well, the answer is a really innovative piece of tech, an intracortical neuroprosthesis. And just like the name says, this isn't a prosthesis for a missing arm or leg. It's a prosthesis that works directly with the brain's motor cortex.
I love this analogy of giving a perfectly timed push on a swing because it's so accurate. The system isn't just sending random zaps of electricity. No, it's way smarter than that. It actually listens for the body's intention to move. It senses the very beginning of a step, and then at that perfect millisecond, it delivers a tiny electrical pulse to the brain that basically shouts, "Yes, that's it. Send that signal louder." And here's how elegant this system is. Let's walk through it. First, electrodes on the leg muscles are listening. Step 2, a little processor predicts the exact moment of intent. Step 3, it zips a signal up to the implant in the brain. And finally, step 4, that tiny pulse gives the brain's own walk command the extra oomph it needs to get through the damaged area. It's this beautiful, closed loop that reinforces what the brain is already trying to do. So, the million-dollar question, does this thing actually work? Well, the very first time they tested this in rat models with spinal cord injuries, the results weren't just good. They were immediate and, honestly, kind of jaw-dropping. Just look at this comparison. It's night and day. On the left, without the device, you see exactly what you'd expect after this kind of injury. The rat's leg is dragging, it can't get any real clearance. But on the right, the moment they flip the switch on the device, that same rat is taking a stronger, higher step. The dragging is just gone. It's an absolutely incredible difference. And the data here is just wild. We're not talking about small, incremental changes. Leg dragging dropped by 36%. Step height went up by a staggering 133%. And the rhythm, the regularity of the gait, improved by 41%. These are quantifiable, massive leaps in function happening instantly. Okay, so an instant boost is amazing, right? But here's the real kicker. The question that changes everything. Could this device be more than just a temporary fix? Could it actually be a training tool that helps create real, lasting recovery, even when you turn it off? Well, that's exactly what they decided to test next. So they set up an 8-week study. For 4 weeks, one group of rats got daily training with this neuroprosthesis. Right from week 1, they were already doing better than the other groups. By the time the training ended at week 4, their performance was way, way better. But the real test, the moment of truth, was week 8, a full month after they stopped the training. And guess what? The improvements stuck. When you line up all the groups side by side, the results are crystal clear. The rats that only got treadmill training or no training at all, they didn't improve much. But the group that trained with the neuroprosthesis, they made these huge, lasting gains that they kept long term. This wasn't just a crutch, it was actually teaching the nervous system how to heal itself. So this leads us to the biggest question of all. What was actually happening inside the brain to make this recovery last? I mean, how was it really healing itself? To figure that out, the researchers had to look deep inside, at the brain's own internal wiring diagram.
So you've got to understand, in your motor cortex, there's basically a map of your entire body. Specific little areas are in charge of controlling specific muscles. Now, after a spinal cord injury cuts off the connection to, say, your leg, that part of the brain's map, it effectively goes dark. The brain cells are still there, but they've got no one to talk to.
And this is exactly what the researchers wanted to track. As they put it, they were looking for an explicit coupling between the physical recovery they could see and the changes happening on that brain map. In other words, could they literally watch the brain rewire itself in real time as the body got better? And incredibly, that's precisely what they saw. A week after the injury, the part of the map for the leg was faint, almost gone. But after weeks of training with the neuroprosthesis, new connections started popping up. The map literally started to light back up. By the end, the brain had successfully built new detours around the injury, reestablishing and strengthening its connection to the leg. And here it is. This is the scientific heart of the whole paper. The physical recovery, how well the rats were walking, and the brain's internal rewiring, they happened in perfect lockstep. As the rats walked better, their brain maps got stronger and clearer. For the first time, we could watch the brain's plasticity, its ability to change, happen in direct parallel with physical healing. The training wasn't just working the muscles, it was physically reorganizing the brain. So this brings us to the final and most important question. We've seen this work wonders in rats, but what could this mean for people? What's the future here? What this all boils down to is a powerful argument for a completely new kind of rehabilitation. It's an approach that doesn't just focus on the body, but brings the brain into the game as a primary target for therapy. It's about using technology to help the brain do what it does best: adapt, learn, and forge new pathways to get the job done. And that leaves us with this final, profound thought. Now, there's still a long road to get this into clinical use for humans, for sure. But this research opens up a thrilling new possibility. Could targeting the brain, the very source code of movement, be the key we've all been looking for to help restore mobility for millions of people around the world? It's an incredible thing to think about.